So, welcome back, and this is lecture number 41. We will be talking about the spanning set. So, to define the vector space, we need to prepare for many concepts, and this is one of them, so called the spanning set. And here we will be talking about the linear span first, and then we will be talking about spanning set. So, what is the linear span? So, linear span of vectors of given vectors v1, v2, v3, vn, this is defined as usually we denote as a span of this v1, v2, v3, vn, and we define as the set of all these linear combinations of these vectors v1, v2, v3, vn. So, here exactly this is the linear combination given lambda 1 v1 plus lambda 2 v2 and lambda n vn. So, this is the linear combination of the vectors, and this lambda belongs to the set of real number. So, this is a set of all linear combinations of the given vectors we call the span of v1, v2, v3, vn. Exactly. So, the collection of all linear combinations is called the linear span of the vectors v1, v2, v3, vn. And the problem here we will discuss now is this vector 1 0 0 transpose, just to tell that this is a column vector, but we can do also with the row vectors. So, here is the vector here in the span of the vectors 4, 2, 7 and 3, 1, 4. So, what do we need to check? Basically, can we write this vector as a linear combination of these two vectors, because this is the question here, that is this vector in the span of the vectors of this. So, what is the span of these vectors? All linear combinations of these two vectors, and to check whether this belongs to this span of this these vectors or not, we will just check whether this vector is a linear combination of these two vectors or not. So, we need to basically check, we need to find the lambda 1 and lambda 2 such that the lambda 1, this vector 4 to 7 plus lambda 2, the another vector here 3 1 4 will give us 1 0 0. Whether this is possible to find such lambdas or this is not possible, the system here is inconsistent or it is a consistent system which can give us the lambda 1 and lambda 2. So, to answer this again, we have to get back to this the idea of the augmented matrix and the row reduced echelon form. Again, just note that this row reduced echelon form is very important. Almost in all lectures we will be utilizing the idea of this solving the system of equations using Gauss elimination, or rather saying this reducing to this row reduced echelon form, because once we have this row reduced echelon form, we can tell exactly that what type of solution we are getting out of this given system. So, here we have, this is the augmented matrix. So, our equations are like 4 lambda 1 plus 3 lambda 2 is equal to 1, the second equation 2 lambda 1 plus lambda 2 is equal to 0, the third equation 7 lambda 1 plus 4 lambda 2 is equal to 0. So, out of it we have written this augmented matrix, the coefficient matrix here 4 3 2 1 7 4, and then this right hand side vector which is 1 0 0. Now, we need to reduce it to the row reduced echelon form, and that idea is also we have explained several times. We need to make this element 0, then this element 0 with the help of this equation number 1, and then we need to make this element 0 with the help of the equation number 2. So, that doing so, I am writing directly here what will be the reduced echelon form. So, 4 3 1 and then 0 here 1 1 and 0 0 2. So, this is the row reduced echelon form, and from here now we can conclude, because this is now our the first column has a pivot element, the second column has also the pivot element, and but the problem here is with the consistency of the equation. The last equation says that 0 is equal to 2. which is not possible here. That means we cannot solve this system, for lambda 1 and lambda 2. There is no solution because our equations are inconsistent, so we cannot get any solution of this given system of equations, and therefore the answer to this question is that this vector 1 0 0 does not lie in this span of the vectors 4 2 7 and 3 2 4. So, here the system is inconsistent, and we cannot write down that as linear combination given there. So, there is another nice result here. We will not go through the formal proof, but we will see at least some intuition how this is happening. So, if S is a subset of a vector space V, then this is span S. Yeah. So, what is span S? All the linear combinations of the vectors, that is the span S. Is a subspace of V, and what is the nice property this span S has? So, we take any vectors, a collection of vectors, and then the span of this will give you the vector space. So, this span S is a subspace, meaning this is a vector space of this V, the subspace of V, whose elements we have taken as the subset, and this is the smallest. Another important information, that this is the smallest subspace which contains this set S. So, there cannot be any smaller subset of this which contains S and is a vector space. So, this is the smallest vector space containing the set of vectors. So, just to see the idea of the proof here. So, we take let us say this is our set S, which contains V1, V2, V3, Vn. These are the elements of this S, and what we will show that the span of this S is a vector space, of V. So, for showing the vector space, we need to show those two properties, because we are talking about the subspace here. We need to absolutely show those two properties, the closure properties. That means you take any two elements of this set, and their vector addition should also belong to the same set, and also when we multiply this set by a number, a scalar number, that the new element should also belong to this set S. So, here let us suppose this U and V, they belong to this span S, and now because U belongs to this span S and V belongs to this span S. So, we can write down this U and V as a linear combination of the vectors V's. So, here the U is written as a linear combination of the Vi's vector, lambda is Vi. So, this is a linear combination. Here also the V we have written as a linear combination of the vector V's. Note that these lambdas and these mu's will be different, and they are the scalars, but this U is another vector. So, this is a linear combination, a different linear combination. Here V is another vector. So, we have a different linear combination there. So, these two vectors which we have taken from the span S, they must be the linear combination of the V's. And now, if we add them, so U plus V, if we add them, so what will happen when we add them? This will be lambda i's plus mu I, and this the Vi. So, again this is a linear combination of the Vi's, because when lambda i's and mu i's are real, their sum is also a real number. So, we have again this as a linear combination. So, this will also belong to span S, because the span S contains all linear combination of the Vi's, and this is a linear combination. So, definitely this will also belong to the span S. And another property, the closure property, what we check when we multiply by any constant, any scalar, like here we have taken the C as a scalar. So, if we multiply this C to this vector U, then what we will get? We will get, so here this C, not lambda I. So, when we write down this U, because U is a linear combination, yeah, well correct. So, this U is a linear combination, so which we have already written here. U is written as the lambda I V I, and when we multiply by a constant here C, by a scalar C, then what will happen? The C lambda I into V I. So, this C lambda I, when we have multiplied this scalar C here to lambda I, that is another real number, and this is another linear combination of V I. So, once we have this linear combination and all the linear combinations belongs to this span S, so this element will also belong to span S. So, what we have seen here, the closure properties are satisfied, that means this span S is a vector subspace. So, span S is a vector subspace, and what else we need to show that that any subspace containing the element of S is also that set will also contain span S, and the reason is clear because this span S contains all the linear combinations. So, if you have a, suppose you consider a vector space, we have a vector space for instance which contains this set S here. So, definitely, because if this is a vector space, let us say W is a vector space which contains S. So, definitely because this is a vector space, all the all linear combinations, because when we add two elements of this must be there. So, eventually all the linear combinations must be there in this set W, that means this will also have a span S, and that itself tell us that span S is the smallest subspace which contains this S, because anything else which contains S will also contain this span S. So, it cannot be that this is not the smallest subspace. So, what we have learned here that this span S, the span S, you take any vectors from a vector space and having this span of these vectors, that will form a vector subspace of that vector V. And there is another one, this is called spanning set. So, what is a spanning set? The set here V1, V2, V3, Vn is set to form a spanning set of vector space V. So, we will call that this is a spanning set of this vector V. If for any V, if we take any element from that vector space V, then there exists scalars this alpha 1, alpha 2, alpha n, such that we have V is equal to this linear combination of these V's here. So, basically we call that this is a spanning set of a vector space V, if any element of this vector space we can write down as a linear combination of this given set V, or in other words which we have written here, the vectors V1, V2, Vn in V are set to span V if every V in V is a linear combination of the vectors V1, V2, V3, Vn. So, this spanning set is very important. Once we have the spanning set, basically we can write down any vector of that vector space in terms of these given, or as a linear combination of these given vectors. So, the example here we are considering the vectors 1 0 0, 0 1 0 and 0 0 1, this form a spanning set of R3, meaning what we have to show that if we take any element of this R3, any element of this R3, then we must be able to write down as a linear combination of these three vectors, and that is what we mean the spanning set. So, let us check whether how this 1 0 0, 0 1 0 and 0 0 1 form a spanning set for the vector space R3. So, for any vector, so we take a general vector this V1, V2, V3, which we have denoted by this V1, V2, V3, that can be any vector from R3. We are not restricting anything on V1, V2, V3. They can be any real number, meaning that this vector belongs to this R3 and it is a general vector. Yeah, it can be any vector from this R3. And what we are supposed to do now, we will show that this vector, which is a general vector from this R3 without any restrictions. So, any vector from R3 we can write down as a linear combination of of these given vectors. And why this is trivial in this case? This is v1, v2, v3, and the structure, this is called the later on we will come up with another name that is called the standard vectors, or rather standard bases, which we will refer later on these terminologies. So, here we have 1 0 0, 0 1 0 and 0 0 1. What we need to do, we need to just multiply this first vector by the number v 1, the second one v 2 and the third one v 3. And as we see clearly, this is the first component here v 1, here we have 0 0. So, basically this will add to v 1, the second one here 0 and there 0, only the v 2 will be coming up, and in the third one when we add, only the v 3 will be coming up. So, this any vector of this vector space R 3 we can write down as a linear combination of this these vectors 1 0 0, 0 1 0 and 0 0 1, which was trivial to see in this particular case. Another example we will be talking about these vectors here 1 1 0 and 1 1 all 1 here. So, 1 1 1 and we have 1 1 0 and we have taken here 1 0 0, and this also form a spanning set of this R 3. How this forms a spanning set? So, we have seen already one example where the vectors were taken as 1 0 0 and 0 1 0 and this 0 0 1. This is another set, and then again we are claiming that this form a spanning set of this R 3. So, naturally this spanning set is not unique. Yeah, we can have a different set of vectors and that span the same vector space. So, here this is another example where we will see that this set can also span R 3. That means, any element of this R 3 we can write down as a linear combination of these 3 vectors. To see this, we will take a general vector here v 1, v 2, v 3 from this R 3, and we will try to write down this v 1, v 2, v 3 as a linear combination of the given vectors, meaning that lambda 1 times this first vector, lambda 2 second vector, lambda 3 the third vector. Now, the question is, can we write down as a linear combination here, because here is not as trivial to see as the earlier case, though this is also not difficult. So, what do? We will solve these 3 equations, the system of equations. The first equation is lambda 1 plus lambda 2 plus lambda 3, the second equation is lambda 1 plus lambda 2, third equation is just the lambda 1 is equal to v 3. So, without indeed reducing to this row reduced echelon form, we can directly also solve this equation. We do not have to do that, because this equation, the third equation, tells that lambda 1 is equal to v 3. So, from here itself we get direct answer that lambda 1 is equal to v 3. Now, we will take the second equation, which tells us that this lambda 1 and plus lambda 2 is equal to v 2. So, from here we will get this lambda 2 as v 2 minus v 3. So, the second equation will give lambda 2 as v 2 minus v 3, and from this equation number 1, which is lambda 1 plus lambda 2 plus lambda 3 is equal to v 1. So, lambda 3 will be v 1 minus this lambda 1, which is v 3, minus lambda 2, which is here given as this is lambda 2 and this is lambda 1, and this was the right hand side. So, from this first equation we got that lambda 3 is equal to v 1 and minus this v 2. So, here also we got the v 1. So, here the lambda 1 is just the v 3, the lambda 2 we need to take v 2 minus this v 3, and this lambda 3 we need to take v 1 minus v 2. So, we got this linear combination here, that this any vector v 1, v 2, v 3 we can write down as a linear combination of these given vectors in the form that v 3 the first vector, v 2 minus v 3 the second vector, and v 1 minus v 2 this third vector. So, again we have seen in this example that this was a different set here from than the earlier example, but again this is also a spanning set of this R 3. So, what we have now, we have this example number 3, where we will show now we have taken from the previous example. Yeah. So, these vectors 1 1 1, 1 1 0 and 1 0 0, these are from the previous example, and we have taken one more, that 1 0 0 1 0 1. So, we have added one more vector here. Now, our set here is bigger, and now again this also forms a spanning set of R3, that is what we will observe now. So, the existing set, and we have added one more, this vector 1 0 1, and this is also forming a spanning set. So, you can have really a different number of elements in the spanning set, exactly, I mean quite different elements also in the set. So, here we will check how this forms a spanning set. So, for any general vector v1, v2, v3, what we have to again consider this linear combination, that whether we can write down this v1, v2, v3 as a linear combination of these 4 vectors. So, we have these 4 lambdas now, lambda 1 plus lambda 2 plus lambda 3 plus lambda 4. So, we have again 3 equations, but there are 4 unknowns. Unknowns are these lambdas, and we have the 3 equations. The first equation is this sum of all these lambdas is equal to v1, the second one lambda 1 plus lambda 2 is equal to v2, and from the third equation we have lambda 1 plus lambda 4 is equal to v3. So, having these 3 equations and then 4 unknowns, we will again set up this augmented matrix. So, our augmented matrix now, here these columns will be these vectors here 1 1 1, 1 0 and 1 0 0 and 1 0 1, with the right hand side v1, v2 and this v3. So, this augmented matrix, we can reduce it to this echelon form, which is, I believe, very simple again. So, here this is the first will remain as it is v1, and then here we will make it 0. So, we will subtract row 1. So, this is also 0, this is minus 1 minus 1, and then we have v2 minus 1. Here again we will subtract that. So, we will get this 0 and v3 minus this v1. So, and now we can exchange these 2 rows, and eventually we will get this row reduced form. So, we have this reduced form here. And now what we will observe out of this reduced form, whether we can get such lambdas or we cannot get such lambdas now. So, getting again back to this pivot elements, so the first column has a pivot, second column has also a pivot element, and the third column also has a pivot element. So, we have the 3 pivot elements, and here we do not have this pivot element, this is not the pivot element. So, this lambda corresponding to this 4. So, lambda 4 is a free variable, right. So, lambda 4 is a free variable, and all other lambdas will depend on this choice of this lambda 4. So, what do we get now? So, the question is the answer to this question is that we do have such lambdas which will add up to this v1, v2, v3, and indeed now in this case we have many choices. We have many choices for these lambdas to give this v1, v2, v3. In fact, it is not unique now, this representation is not unique. While in the earlier cases one can closely observe when doing this echelon form. So, what we will get, we will not get this column, for instance, if we consider just with these 3 examples. So, we will get these, every column will have a pivot here, and that will be equal to the number of these unknowns, the number of lambdas in that case, and we will get a unique representation. So, in earlier example when we did not have this vector there, we have the unique representation of this v1, v2, v3 in terms of the given vectors. But what happened now in this case, we do not have a unique representation, but we can represent it, we can write down any vector from this R3 in terms of these given 4 vectors. So, indeed this is a spanning set. The only difference from the earlier example to this example here is that we have a non-unique representation, that we have to choose now lambda 4 and then compute lambda 1, lambda 2, lambda 3. we have basically infinitely many solutions now. So, this is a non-unique representation. In the first two examples, we have a unique representation. So, that was the difference here, and now in this case we have a non-unique representation. Coming back to this example 4, we will see that again we have 3 vectors here, 1 2 3, 1 3 5 and 1 5 9. These are 3 different vectors. So, but they do not span R3. In example 1 and example 2, we have 3 vectors and they span R3, means any vector of R3 we can write down in terms of those given vectors. So, in the example 1, we have this set here 1 0 0 and 0 1 0, and then we had 0 0 1. So, these were the 3 vectors from example 1. Example 2, I guess it was 1 1 1 and then 1 1 0 and then we had 1 0 0. So, this was from example number 2. So, with these, though they have the 3 different elements from R3, but they span R3, means any element of R3 we can write down in terms of these vectors or in terms of these vectors. But now in this case what we will observe, that this is not possible that you take any 3 elements from R3 and that will form the spanning set. How to check this? We will take a general vector here V1 V2 V3 as usual, and we will try to write down this V1 V2 V3 in terms of the lambda 1, lambda 2 and lambda 3. So, lambda 1 with the first vector, lambda 2 with the second vector and lambda 3 with this third vector 1 5 9. So, writing this in terms of the lambdas, we have the augmented matrix here now, the coefficient matrix. So, this 1 2 3, 1 3 5 and 1 5 5, the right hand side here V1, V2 and V3, we need to reduce to the echelon form. So, we can make this 0 by multiplying this 2 times and then subtracting here the 0, and then we will get here 1, and then here we will get 3, and then V2 minus this 2 V1, and then again we have to also do this manipulation later for this case. So, just to give you the idea, the first row we have this one, the second one, the 2 times of this we will subtract. So, this is 0, this is 1, 2 times. So, here we will get 3, and this will be 2 times minus V2 minus 2 V1. The third one 3 times or R1 we are subtracting. So, here the 2 and the 3. So, here we will get 6, and here V3 minus 3 V1, and then once again this 2 times of this we will subtract. So, this will become 0, this will also become 0, and here this factor will be coming. So, this is the row reduced echelon form which we got here 1 1 0 and 0 1 3 and 0 0 0. So, now what do we observe in this case, that here we have pivot, here also we have a pivot, and thus forget about the pivot, we have the inconsistency here. While inconsistency, because this V1, V2, V3 they can be any real number, because our vector here is from R3 and it is any arbitrary vector from R3. So, having so, we cannot just observe that this will be 0, this will be a non-zero number as well in many situations, and then 0 is equal to something non-zero we are getting. So, this system we cannot solve for general V1, V2, V3 from R3. That means the system is inconsistent, and hence we cannot write down in this case as a linear combination of these given vectors. So, what we have observed, that just the number is not important, that we have taken here 3 elements from R3. In the third example we have taken 4 elements from R3. In first 2 examples we have taken again only 3 elements. In the first 2 cases we had a unique representation for a given vector from R3 in terms of the given vectors. in the third example, where we have taken 4, that was also a spanning set, but there we were getting non-unique representations of a given vector from R3. And now in this example, though we have 3 vectors from R3, but they are not sufficient to represent a general element or a general vector from R3. So, this does not form a spanning set of R3. So, there is a lot more to discuss on this spanning set, and that will follow in the next lectures. Here the conclusion is that this linear span is nothing but all the all linear combinations of the given vectors, and the spanning set which v1, v2, vn of v, we will call that this is a spanning set if any vector of this v we can represent in the form of these vector v's, then we call that this is a spanning set. So, these are the references used for preparing these lectures, and thank you very much for your attention.